The 1960s produced some of the greatest technological feats of the 20th century, and one of them was Concorde. While America was aiming for the moon, Britain and France were reaching for the skies, with an airliner that would fly at over 1,300 miles an hour. This project was one of the most challenging ever in civil aviation.
And it produced a truly iconic plane, and one that is still capable of creating emotion in people. I remember when I was a student in Reading, right underneath its flight path, hearing the sound of those engines ripping across the sky, seeing this wonderful needle-like shape heading off to exotic locations. But unfortunately, never with me on board.
I'm going to be looking at how Concorde pushed the aeronautical boundaries far further than any other airliner had done before.
Now, I'm an archaeologist, so I'm normally used to dealing with far more ancient relics than Concorde. So this story is going to be a bit of a departure for me, because not only is it set in the 20th century, but many of the people who designed and built Concorde are still alive today. So meeting and chatting with them is something I'm really looking forward to.
I'm also going to be looking around Alpha Foxtrot, the last Concorde ever built, at its final resting place in Bristol, and using computer-generated images to get inside parts of it that you never normally see.
The origins of supersonic flight came just after the Second World War, when engineers were keen to push planes to higher and higher speeds. Before that, the closest that planes had got to breaking the sound barrier was when they were in near vertical dives. And at those speeds, the pilots experienced such incredible handling difficulties that some people thought that this was one barrier that would never be broken.
But it finally was in 1947 by an American, Chuck Yeager. Soon after, Britain was developing supersonic fighters like the Lightning, and from here, the next logical thing to do was to make airliners that would break the sound barrier. The first problem in designing a supersonic airliner is deciding the shape of the wings. Professor Ted Talbot worked on some of the first British wing designs.
And you can see there that there's been nothing flying like that ever.
That's a very weird shape, isn't it?
It is, isn't it? Yes.
That's the 1st of February, 1957.
Yes.
I didn't realise that the origins of supersonic civil transport went back over 50 years.
Oh, they'd been whispered for a long time, and the first formal meeting called by the Ministry of Supply was in November of 1956.
So it's got this peculiar sort of W-shaped wing.
If we had the wing continuous like that all the way back, it would be touching on the ground at takeoff.
Right.
Which isn't advisable. So the thing to do was to put these kinks in it and bring everything around the centre of gravity, like that.
So would that have flown?
You seem a bit hesitant about that.
Well, I am. Yes, it would have flown. Whether it had been useful as a passenger aircraft, I don't know.
Right. So this never got beyond this stage, did it?
No. We didn't like it anyway.
By the early 60s, the designers had moved away from the more unusual and settled on the Delta wing for their supersonic airline. At this time, the English, French, Russians and Americans were all scrambling to develop their own supersonic airliners. To try and be the first in the air, an Anglo-French agreement was signed in 1962 to pool their resources and build Concorde. Many of the designs for Concorde were drawn at Filton in Bristol. Alan Perry was a draftsman right at the start of the project, working on the wings of the prototype.
One thing I find very difficult looking at something like Concorde is trying to get my head around the idea that it was built before the age of computer design, that you actually had to sit and draw everything out and experiment.
That was the only way that we could actually do the design work. And certainly the paper design lent itself to paper models. If you could produce a cardboard model of the thing in 3 dimensions and people could look at it, from different views, this was a great help.
Right, OK, let's see if it flies. That's pretty good.
Not bad.
I'm impressed. The landing wasn't too brilliant, was it?
No. It was quite common to see us up behind the Brabazon hangar, up on the slope, throwing small models made out of used time cards that people used to clock on.
I think we ought to have another test flight in a minute, but I'm still really impressed by the fact that you use things like this to design that.
Well, I'm a great believer in 3-dimensional modelling, and I created a title for it. It was Very Low Technology, Virtual Reality. This was something I enjoyed, always have, always will, that you can take something so ordinary as a piece of cardboard or a piece of paper and make something out of it which is useful and contributes to the project.
People tend to think of designing something like a plane as being just a pure science, don't they? But do you think there's a bit more of an art in it as well?
Well, I always felt there was certainly an artistic element in what we did. I think possibly because of the shape of the aeroplane, the art form came across quite easily. I defy anyone to look at Concorde and not marvel at the shapes that they'll see.
Oh, look at that!
Better.
Brilliant.
Better.
Brilliant.
After the wing designs were drawn, the next stage was to put scale models into a wind tunnel. Over 300 different shapes were tried out, with much of this testing being done at Filton. Mike Marsden worked in the wind tunnels, developing and refining Concorde's delta wings.
Because a basic delta is a triangular shape, isn't it?
Would look something like that. But a much better shape for flying supersonically is what we call a slender delta, which is much longer and has much less wingspan, so it might look something like that. And a variation on that would be what's called a Gothic delta, which would look a little bit like that. And this is shaped like a Gothic arch.
So we're getting very architectural here.
Yeah, that's right. And another variation is the OG, which looks a bit like an upside-down wine glass.
Right.
The slender delta and the OG both look quite promising. And in the end, the OG was rather better in terms of balance.
Because presumably you've got to get to a balance, haven't you, between something that's going to go very, very fast if you want to make it go supersonic, and something that is going to be stable and handle well.
That's right, yes.
And also land.
And take off and land, yes, that's right. And that was the major problem, of course. This OG wing's ideal for flying supersonically, but it's on the face of it, it's not a very wonderful thing for low speed, for taking off and landing. But it was found that if you gave it a very sharp leading edge, that's this bit here, you could make it work. With this very sharp leading edge, it's quite different. They tore the rule book up, if you like, and the airflow is quite different, behaves quite differently. If this is the leading edge of Concorde and the air's coming up here, it can go underneath quite happily, but it can't follow this sharp leading edge round here, and it lifts away, it breaks away, and we call this separated flow, and it separates like that.
The separated flow coming off the leading edge of Concorde's wings joins together to create low-pressure vortices above each wing. It's these that give Concorde its lift at low speeds.
A major concern for Concorde's wing designers was how these vortices would behave in a crosswind, particularly at slow speeds like takeoff and landing. Their biggest fear was that a crosswind would cause a vortex to detach, meaning that the wing would instantly lose lift.
to see if these fears were founded, many more tests were done, and a small plane was built to see how delta wings reacted at low speeds. Eventually, the designers' fears were put to rest, and they were reassured that Concorde's wings wouldn't suddenly lose lift at low speeds.
The clever thing with Concorde is you've got this shape which is pretty good for flying supersonically, and the same shape without any change in geometry can give you enough lift, just about. It's not very wonderful, it does the job though, give you enough lift for landing and takeoff.
So, after ideas, models, redesigns and thousands of hours of testing, Concorde finally had safe, effective wings.
But they're just one of the problems that you've got to overcome when you're building a supersonic airliner. The next one is, how do you get the plane off the ground? And once you've got it off the ground, how do you keep it flying at the speed of a rifle bullet? Now, to do that, they needed a very special power plant.
There are 4 sections to Concorde's power plant. First are the air intakes, leading into a conventional jet engine. Then come the afterburners, and finally the nozzles. All of these 4 elements had to work in perfect harmony if Concorde was going to be able to fly across the Atlantic at twice the speed of sound. In charge of designing the air intake systems was Professor Ted Talbot.
How do you actually propel it up to speeds of, 1,350 miles an hour using a conventional jet engine?
Well, you have to give the conventional jet engine the conditions that it likes, even though you're flying at that high speed. So you have to slow the air down scientifically from where it comes in to where it gets to the engine itself. This is really a subsonic engine developed to last at supersonic conditions. And most supersonic aircraft have subsonic engines in them.
So what happens if air goes into an engine like this at supersonic speeds?
Well, the engine will simply malfunction.
So it seems to me that this air intake was actually crucial then to getting Concorde flying efficiently at supersonic speeds over long distances.
If this had failed, then the rest of the aircraft would have failed as well. And it was because we were able to do this, and lots of other people weren't, that we managed to get the Concorde going across the Atlantic.
What's also amazing about these intakes is that they had to work across a vast range of speeds, from standing still to twice the speed of sound. Now, to see how this is done, I need to go on a virtual Concorde flight, but standing inside the intakes.
These engines need the most air on takeoff, and so the ramps up here are raised, and an extra inlet opens up down here, allowing even more air to rush in. As the plane approaches something like 70% of the speed of sound, that's just over 500 miles an hour, there's now so much air coming in from the front of the engine that you don't need that flap anymore. That one can shut down. But as Concorde reaches the speed of sound, the drag really starts to build up. And the best way of pushing the plane through this barrier is to light up the afterburners down here. This produces masses of extra thrust all in one go. It's just like strapping rockets onto the wings.
As the plane approaches the sound barrier, a really interesting phenomenon happens, which eventually creates the famous sonic boom. Any object being pushed through air creates a pattern of pressure waves that radiate out from it at the speed of sound. As Concorde gets nearer and nearer to the speed of sound, these waves start to bunch up, until at the sound barrier they merge into one. The sonic boom is essentially this combined pressure wave hitting your ears. With Concorde now through the sound barrier, the afterburners are turned off as the drag starts to fall again.
The problem now is that the engines just don't work properly. There's simply too much air being rammed into them. It's got to be slowed down. And this is where one of the really clever design elements of Concorde comes in. All to do with these ramps above me. Now, at about 1.3 times the speed of sound, they start to be gradually lowered, forcing the air into a series of shock waves that build up along the length of the top ramp and focus down here by the bottom lip of the intake.
As the speed increases, the flaps are lowered more and more, until the cruising speed of 1,350 miles an hour is reached.
Each shock wave that the air passes through slows it down a bit. So by the time it reaches here, it's got down to just below 650 miles an hour. Now this is where the rear ramp comes in, expanding the air and in the process reducing its speed even further, so that it goes into the engine at around 350 miles an hour. This is amazing. Between these two ramps, they've taken air in at 1,350 miles an hour and sent it out at 350. That's reducing it by 1,000 miles an hour in 11 feet.
Concorde has now entered into the flight phase known as supercruise, where only 8% of the thrust is generated from the engines, 29% from the nozzles at the rear, and an amazing 63% from the intakes. This is where the delta wing and the power plant are working together at their best, allowing Concorde to fly efficiently at just over twice the speed of sound.
Once Concorde reached supersonic speeds, it effectively became a rocket. But you still had to keep it flying straight and level. Now, with a conventional plane, you'd do that using flaps. But you couldn't use flaps with Concorde. They'd have caused too much drag. So what the engineers did was to design an ingenious system that used fuel.
But most of the ones in this pack are...
Alan Perry worked on the fuel systems for Concorde and also has lots of the original plans.
One of the things I'm very intrigued about is I have always thought that fuel was just there to propel a plane.
Yes.
But you worked on the fuel system and it was used for something else, wasn't it?
Yes, indeed. If I could just take these drawings away. Right. This is the plan view. Right. And on this plan, you'll notice these shaded areas are labelled reservoirs, and they're all the fuel tanks that were installed in the Concorde wing and in the fuselage. Okay. There was only a small amount of the wing that wasn't full of fuel, so the wing is, for all intents and purposes, one big fuel tank. It was discovered quite early on that with this type of wing, this sort of delta wing, there was an aerodynamic feature that had to be catered for. So when the aeroplane takes off, in the first instance, the trim tanks at the front of the wing will be full of fuel.
Right.
When the aeroplane gets into the supersonic regime, the effect is to take the average lift on the wing, it moves back. It's just one of the things that happens, with this type of wing. And the result of that is that the aeroplane becomes nose heavy because the lift is moved further back and the centre of gravity is where it was. So the lift now is going to tip the aeroplane's nose down. The answer to that is to transfer the fuel in these forward part of the wing here and under the floor into the back of the fuselage where this other tank is.
By doing that, the centre of gravity moves back, balancing the new centre of lift.
So it's a sort of balancing act then, is it? You're having to keep it tuned throughout the whole flight?
Yes, for the most part, the flight engineer who sits behind the pilot and co-pilot is in charge of the fuel management system, and he has the last word. He's monitoring all the automatic systems that are being carried out.
So he sits there in front of that panel with all those dials on it, does he?
Rather like an organist.
Yes, it is a bit like that, isn't it?
Yes.
Sort of going, right, we'll have a bit from here to there, to there, to there,
That's
just to
right,
keep the whole
yes.
thing flying level.
Yes.
A lot to think about, though, isn't there?
The engineer is a very busy man.
Yeah. The pilot just sits there and steers it.
When Concorde slows to come into land, the centre of lift starts moving forward, and so the fuel is then pumped into the tanks at the front, still keeping the plane perfectly balanced. At the end of the flight, coming into land presented one final problem for the engineers to solve.
And this is where elements of Concorde's design proved a problem. Because of the shape of its wing, it meant that it had to come in at what looked like a very, very ungainly angle, very steep, with the result that the pilots couldn't see the runway. Now, short of putting a glass floor in the bottom of the cockpit, there was only one way around that, and that was to hinge the nose down, which was what gave Concorde its very distinctive droop snoot.
Somehow, it seems fitting that the last Concorde ever to land was here at Filton, where so much of the design work took place, and where Alpha Foxtrot now sits, never to fly again.
You can't deny, though, that Concorde polarised public opinion. It used a lot of fuel, and it made a lot of noise, but to some people that noise was just part of its great appeal. So, here you have it. Concorde, one of the great engineering success stories and a true icon of the 20th century. What a plane.
Become a Teachers TV associate to get the latest news, gain access to new programmes before anyone else, and have exclusive access to clips and programmes for CPD and presentations. Teachers.tv/associates.